All right. Well, yeah. Thanks, Remy, Martin, all the organizers, and everyone for coming. I'm really excited to do this, and this is my first time actually teaching like an interactive thing like this. So I wrote some notes, but I'm not sure how this sort of thing goes live. So learn with me. I'm also not sure the level that we're all at here because we're coming from so many different areas of math and illustration. So I'm gonna try and cover a fair amount of stuff in the course to try and teach you about like what these tools are capable of. And then we're gonna have examples on the homework that are at all sorts of different levels of difficulty so that hopefully we can find things to work on together in groups. So the first thing I want you all to do, I know there's been some trouble with the internet if people are not logged in, but if you do have internet connection, go to shadertoy.com right here and make yourself an account. Even if you don't have an account, you can play around on here in lecture. What we'll do is once you're in, we'll click over to new and we'll have a little tab like this where you can type code. And we'll type all our code online in the browser. But if you have an account, you can save it and that'll be good for the homework because then you can like look at it from before. You can go back and look at all your pretty pictures a month from now and be like, wow, that was so fun. I remember when I drew a square in lecture. It was amazing. So yeah, put together an account now and that'll help. And while you're doing that, let me see. I'll also put up here, I wrote some notes to go with the course because I know it's a lot of material when you're learning new computer stuff. So if you go on the Discord, Remy has the link there. Also, if you go on my website, it's shaders.stevejtrettel.site. And you'll find the notes and like all the example code that goes with lecture and so on. So there's a reference online for y'all. All right, so yeah, while you're making the account, the mini course is called GPU Accelerated Mathematical Illustration. And I love writing images this way, like pixel by pixel with the GPU. I wanna show you a couple pretty things first, like things we like to think about I'm a mathematician in low dimensional topology geometries, like hyperbolic tiling. So like here's a nice hyperbolic tiling. The Poincare disk, like two models on the Riemann sphere, like inside one disk, external to the disk, the other model. You could do a conformal transformation, draw it in a band or something. We'll look at this in a couple days. The difference between the program that writes these two is like just like 2 or 3 lines of code. So that's a good plug for learning to think this way. You could do it in 3D. This is work with Remy and Henry and Sabetta here. So here's a 3D tiling. I also like to make all sorts of other illustrations. So here's some atomic orbitals for a piece called Spectra I made for our university. And so it's solving the Schrodinger equation using the GPU, and then ray tracing through the solution to the Schrodinger equation. So you find the probability distribution, like add it up along each ray. And that gives you the probability that you'd intersect the electron there, and then you shade by that. Drawing fractals, that's a classic. Everybody likes drawing fractals. So here's a take on the Mandelbrot set we'll look at. The Mandelbrot set is a parameter space in complex dynamics. It's a parameter space of Julia sets. So each point on the Mandelbrot set corresponds to another fractal, the Julia set, and can draw them all next to each other and see the whole big picture emerge. We'll draw this tomorrow. So some of the stuff we'll see. Let me see. 3D fractals. 3D is fun. We won't draw this, but my goal is that we will learn how these sort of things are drawable. We'll learn the tools, like how do you represent a fractal in the computer this way? How do you represent rays so that you could try and intersect a fractal? Like how do those sort of things work? Some nice algebraic surfaces, maybe easier than a fractal. This one you might recognize from the wall here. I saw the posters when I walked in and I was like, perfect, I'll make one of those. Some other surfaces. And then we won't do this during the course, but once you learn how to compute this sort of thing, there's many avenues you can take in your own work. So things I like doing is thinking about lots of stuff in curved space. One thing I don't like doing is taking really long flights. So before I flew to make myself feel better, I simulated a wormhole from San Francisco to Paris, but then I couldn't go, so I had to take the plane anyway. So there's limitations as well, but sometimes just in theory isn't enough. But okay, so that's where, that's the sort of images we're gonna talk about. There's the sort of images you can make using this sort of GPU programming. The main idea that I wanna talk about is how these images are produced. So day one on our notes here is called pixels. Let me see, I actually did make some slides for day one. No, I don't think I'll do it. So pixels, because the rendering is pixel-based. So instead of drawing a curve by first computing all the points along a curve and then connecting them by lines and then telling your computer screen where to put those lines, like storing this curve inside your computer in some sort of a data structure, and then being like, okay, here's the data, now put it on the screen. We're just starting with the screen. We're saying, like, what is a computer screen? A computer screen is just a bunch of pixels. What do I need to put an image on a computer screen? I just need to tell each pixel what color it should be. So I need a function that like takes a pixel and it tells me a color. And for math people, this is great, right? Because like the screen, bunch of pixels, is like R2, or like really is like a discrete grid by discrete grid, right? And then what's a color? I want a function to color. Well, our eyes are pretty bad. Evolution only gave us 3 types of cone cells, so our eyes can see 3 colors. Yeah, if you're lucky. If you're lucky, you could get all the way up there to 4. And computer screens take advantage of this poor behavior on evolution's part and represent all colors on the screen using just 3 LEDs. So to specify any color on a computer screen, you just need to give a red, green, and blue. One nice choice of basis for color space. And so what is an image on a computer thought about mathematically? It's a function from R2 to RGB space. We're gonna put RGB in bounds, like your screen is actually doing this with an LED, right? So it's like 0% brightness up to 100% brightness. Computer, like we can't draw every image on a computer. Like I can't draw a realistic picture of the sun, because like the sun fries my eyes, but my computer can't fry my eyes. So there's a intensity cutoff. So red lives in the unit interval. Why not? Unit interval is my favorite interval. Maybe some of you like the interval 0 to 255 or something, but like red, green, and blue all live in the unit interval. So this is gonna be a function from R2 to the unit interval cubed. Oh, talking too much, the computer thinks I'm done. I'm not done. Come back. I'll wait for it. Okay. So this is the sort of object that we're going to be writing. We're going to learn how to write code that just writes down functions from R2 into the unit interval cubed, thought of as red, green, and blue. Shader Toy as a platform is a really nice thing for doing this. Your computer does this all the time. Like your computer is doing this when it's drawing the screen right now. It has to big, complicated calculations are going on deep inside of the magic box that we call our computers. And at the end of the day, the magic box goes, hey, pixel that's 517 pixels over from the top and 3 pixels down, that's part of a folder. I'm gonna color that blue. So your computer's doing this every time it's drawing your computer screen. But we're just gonna kind of co-opt that power and be like, okay, don't draw the desktop anymore. Don't draw Microsoft Word. Don't draw tech. Instead, just do whatever function I tell you to do. I'm gonna program the function by hand, and I'm just gonna like take over the computer screen. And Shader Toy is a nice platform for this because it abstracts away all of the difficulty of going into your computer and be like, no, give me the screen, like taking it away from everybody else. It provides you a nice interface where it builds a little fake screen here, like a simulated screen in the browser. And then it has the code here that runs on that screen. So everything we type in, yeah, for me, mathematically minded, I think this is really nice because everything we type in this box here called image, this is what we're gonna call an image. An image is a function from screen to colors. And so at the end of the day, whatever goes in this box has to just be a function from screen to colors. The traditional name, the name that ShaderToy forces on you so that it knows that things are running well, is main image. And so when you open a new, first let me check, is everyone who has internet, are people on ShaderToy? Is anyone, if you haven't found where to click this, I forgot to say, you click the new button up here to get to the screen I'm at. So go to new, and then you should be here. It drops in this code for you automatically. And the reason is because the different parameters here have special names that are given to us. So main image is the name, is the function. And then we need a name for our input space. R2, these are our pixels, right? And these are our colors. The name for the pixels is right here. Frag chord is a kind of strange name. Fragment is the name for a pixel on the screen, and chord is short for coordinate. So frag chord is like robot speak for pixel. So frag chord. And the pixel coordinates start, if this is your computer screen here, 0, 0 is in the bottom. And then the y-axis goes up. And then the x-axis goes here. So it starts with the bottom of your screen is the origin of your coordinate system. The origin's not in the center of the picture, it's at the bottom. So then over here is like, let's say you have an HD monitor, you're like way back in the day. So you have like 1920 pixels that way, and then 1080 pixels this way. So this coordinate would be like 0, 1080. This would be 1920, 0. It counts over pixels like that. So that's the name of the input. The name of the output is frag color. And so I just told you that colors came in triples RGB. And then also that frag color is supposed to be my color. But if you look out here, see in front of it says vec4. Vec2, this is going to be a 2D vector. That makes sense for our pixel, right? X and Y coordinates. But here there's 4. The fourth one is transparency. Like maybe you're putting multiple images on top of each other in a computer and you want something transparent. We're not going to worry about that at all. So it's red, green, blue, and then transparency, an alpha value. That's just going to be set to 1 all the time for us because we're just drawing one image. So we're just going to set the first 3 coordinates. But your computer actually has 4 for color. And then inside of this function, you're allowed to do literally anything you want. So I'm going to delete whatever they wrote. And let's make an easy function. I do need to assign at the end of the day frag color. That's the goal, is to tell the computer screen what color to be. So I got to write frag color. And I'm going to make it equal to something. I know frag color is a vec4. So I'm going to write vec4. And then in there, I have to put a collection of numbers. So red, green, blue, and transparency. Let's make the screen bright red. So I'm going to make the screen 1, 0, 0. So 100% red, 0% blue, 0% green. And then 1 for opaque, like 100% visible. Once we got that typed in, you can hit play at the bottom here. That will compile the program. That'll take this program and like ship it over there. Let's see. There we go. Wrote the constant function from R2 to R3 that just sends it to the unit basis vector 0, 0, 1, but interpreted in computer land, that turns the whole screen red, right? Okay, let's make the screen, let's go back to kindergarten and do color mixing. What is red plus blue? So 1, 0, 1. There we go, nice. So you can mix colors in the linear space of red, green, blue by just thinking about the x-axis is red, y-axis is blue, is green, z-axis is blue. Mix them together. And then 1, 1, 1 will give you a whole white screen. So, couple annoying got-yous about this type of programming, if you are not used to it, is one is everything ends in a semicolon. So you see I typed a semicolon right at the end of a line here. You have to put a semicolon at the end of every line, otherwise it's gonna get mad at you. Another is when you use numbers. Sorry, I should do this precisely here. It doesn't matter right here, it didn't give me an error, but if you write numbers outside of vectors, like most of the time when you write numbers, you have to put decimal points after them so that it knows it's a floating point number. It's not smart enough to like look at something and guess if it's an integer, which is kind of a good thing because you want to tell it when it's an integer versus when it's a floating point number. But the way you tell it is by putting decimal points every time you want to type a floating point number. So those are two things to watch out for. The other good thing about Shader Toy is it'll warn you. Like if you do that wrong, it'll make a line red and it'll be like, hey, this isn't working. And for me, it's like always a semicolon and a period. I still forget those. So, okay, so that's how we start running things. Let's try and make a more exciting image. What I want to do now is I want to make half the screen red and half the screen blue. So instead of just typing in here frag chord equals one color, let's think about how we would do that. If I want to divide the frame left to right, I care somehow about like the x coordinate of pixels, right? Like after a certain number of pixels, I want to change the color. Instead of doing it half to start with, let's just say let's color the first 100 pixels. I can see my screen is 640 by 360, right? It's telling me right there, bottom. But let's just say I want to color the first 200 pixels red, and then I want to color the ones after that blue. So my pixel is frag chord. So if I want to go 200 over, all of the pixels over here have frag chord dot x less than 200, say. So I'm going to type an if statement. I'm going to say if frag chord dot x is less than 200, 200 with a period after it so that the computer doesn't yell at me. Then I'm going to set the color to something. Let's set the color frag color equals vec4. Let's make it red, 1001. And then if that doesn't happen, so if with curly braces gives me what I want to do when frag chord.x is less than 200, and then else, I'm going to color it something else. Now let's color it green. I said blue on the board. Let's not lie. Frag color equals vec4 001, 100% blue, and not transparent. All right, let's see. Oh. There we go. Nice. Thank you for catching the typo. I should be running the agent browser in the background to be fixing my scubes and my chords. All right, so there we go. We wrote now a piecewise constant function, right? We're writing functions from R2 to R3, but we said, okay, just check the x coordinate on R2 and then assign piecewise constant based on that. Now, if I want to go halfway over to the middle of the screen, I could look here. Shader Toy tells me the resolution. If you see on the bottom, it's telling me how many frames a second it's running, and it's also telling me 640 by 360. So I could look at that and say, oh, it's 640 wide. I could divide that in half. And for this exact screen size, that would then put my line right in the middle of the screen. But what if I change the size of my screen? What if I made my browser bigger? And I was like, oh, I know 640 divided by 2 is, I do know this, 320. then I set it at 320, but then I make my screen full screen. It would only draw the first 320 pixels to be red, right? Because that's what I told it to do, and it's going to follow directions. So if I want to say half the screen, I need a way in the computer to talk about half the screen. I need to be able to say what is the screen resolution. And ShaderToy has built into it a couple of variables that get passed to the program that you can use. I'm going to make a list of them on the sideboard here so that we have them around. All of them start with the letter I, lowercase I. So one is I resolution. One is called I time. And one is called I mouse. So I resolution is a variable that's available to us inside of the program. It gets passed from the computer into ShaderToy for us, and it gives us the resolution of the screen. So its x coordinate is the number of x pixels. Its y coordinate is the height of the screen. I time is the computer clock. It's measuring in seconds since you started running the program. And then I mouse is the position of your mouse. So we'll explore both of these later on during today. But starting with I resolution, oh my goodness, wake up. This line halfway through the screen is when my pixels have reached halfway across, which is now I resolution.x, that's the width of my screen, divided by 2. 1/2 width is I resolution dot x over 2. So, okay, let's go change our conditional. Over 2 period. I didn't do that on the board because the board won't yell at me, but the computer will yell at me. I resolution dot x over 2. There we go. Now it's halfway across the screen. I could change those to y's and then do it top to bottom instead. I resolution.y would give me the height of the screen. Fragchord.y would make my conditional depend on the y coordinate. And you could write down a linear function too, right? Like if I wanted to color an arbitrary half plane red and the other side green, I could write down like ax plus by equals c. I could write down such a function using fragchord.x as my x coordinate, fragchord.y as my y coordinate, and then color the screen diagonally or by some angle. But if you actually try and do that in practice, it's going to be kind of annoying because to make it the right size for your screen, you're going to have all these iResolution.x's, iResolution.y's floating all over the place in all of your formulas. You have units everywhere, and I don't know about you, but having units everywhere, not my favorite thing. So we'll leave that to the physics conference. And instead, what we could do is we could build ourselves nicer coordinates on R2, like some nice math coordinates to start with. Like let's normalize things. One, I don't know, I kind of like having the origin in the middle. Like that's easier for me to picture sometimes. And I don't like when my x-axis scale is in the thousands or here in the hundreds. Like I'd like to see maybe a smaller amount of x. Like if I tried to draw the unit circle in pixel coordinates here, like I drew x squared plus y squared is less than or equal to 1 or something, that would draw me like 1 pixel, right? Because I'm measuring things in pixel coordinates. I'd be like way zoomed out. So let's fix that. Let's try and write a function that will make this easier to use. So at the very top, inside of main image, I'm going to make a new variable. I'm going to call it uv for coordinates on R2. So this is going to be vec2 uv. And I want this to maybe scale everything so the x-axis and y-axis are between -1 and 1. So right now x goes all the way up to iResolution.x, y goes up to iResolution.y. So I'm going to divide all of my coordinates. So frag chord divided by Let me write this out properly. We want to make a 2-dimensional vector, so we're going to output vec2. Inside of there, I need to give you an x component and a y component. My x component is frag chord dot x divided by I resolution dot x. And my y coordinate is going to be the same thing, but with y's. I'll get rid of everything else. So once I've done that, now uv, that vector, its x coordinate goes between 0 and 1. And its y coordinate goes between 0 and 1. So I've just done an affine map to the unit square. That's probably changed my aspect ratio, right? This is not a square, this is a rectangle. So we'll deal with that in a bit. But right now I've just mapped everything to the unit square because I'm happy when I'm at the unit square. If I'm at the unit square, it's easy for me to center, like 0, 0. How would I center that? I just subtract by 1/2 and 1/2. So if I want to make this centered at 0, say uv is now going to be equal to uv minus vec2 of 0.5, 0.5. And so now uv stores numbers between -0.5 and 0.5. And now if I write my function, instead of using frag chord directly, I can just use uv as the input to give me color. I can write stuff in terms of uv, and I can get my color. So let's say if uv.x, uv is a vector, right? So its x component is my x coordinate. If uv.x is less than 0, period, then let's color it red. Frag color is equal to vec4 1 0 0 1. And then otherwise, let's color it green this time. Vec4 0 1 0 1. Okay, what's going to happen when I hit run, other than an error because I forgot something? If uv.x is less than 0, my screen's centered at 0, that's going to give me half the screen, right? There we go. So we got half the screen, and we don't have to think about the resolution anymore. We buried that all in setting up our coordinates, and now we can talk in terms of like percentages of the screen. So uv is measured in a more useful way. Well, let's draw something more fun than half the plane. What's more fun than half the plane? A circle's more fun than half the plane. Let's draw a circle. Okay, so I want to draw a picture, and I want to make, let's make the Japanese flag. So let's make a red circle on a white background. So, all right, so what can I do? I have uv. uv is on my plane centered at 0, 0. So I want to draw a circle centered at 0, 0. So I'd like to measure the distance from 0, 0 using uv. And if it's less than a certain amount, then I'll color it red. And if it's greater than a certain amount, then I'll color it white. So let's make a variable. Let's make a variable that measures the distance from the center. It's going to be a floating point number, not an integer. So we're going to call it float to give the type, just like we gave vec2 when it was for those of you coming from programming languages. Oh, thank you. Thank you. Yes. Or does that not work so well? Okay.
So if you want to,
yeah. Whatever's best for y'all, let us know. Okay, this is better. Okay, so let's make a float. Let's call it dist. And this is going to measure the distance from the origin. So I'm going to write it out all the way. So good old Pythagoras taught us how to do this, right? Square root of x squared plus y squared. So x is uv is my point. So uv.x.
is there a comment character?
Is there a what?
Is there a comment character?
Oh, yes, 2 backslashes are comment. Good question. It doesn't seem like what I was about to try works. So, no.
There's star.
Yeah.
Star and then star slash.
But I don't know if you can highlight and then do it, but you could type that. Yeah. Oh, yes. I think you can. I think I should check that here. I think you can do that here. I'm going to replace this with a shorter function in a second. So I'm just typing it out so you can see how math notation works. GLSL has a bunch of built-in functions. One of them is called length. So I will delete this line in a second and write length. But I just wanted to show, if you want to type math functions, GLSL has a bunch of math functions built in, and they're all written in lowercase. And the way we access them is with parentheses. So square root here is lowercase. And then I have parentheses for my brackets. So square root, sine, cosine, log, exp, all of that stuff works with that lowercase and parenthesis notation.
So is this like automatically a function of UV or is it like that?
Good question. Yeah, so it's just, I'm just computing a number here, but the number depends on u and v. So it's all inside of my one big function. And so inside of that big function, the big function is just a function of its invariable, which is frag chord. And everything in here just depends on frag chord. So yeah, dist is just a number, and it's running this pixel by pixel. Like each pixel, it's running this in parallel. So for a given pixel, we now know the distance from the origin. If dist is less than 0.25,
Does your indentation not matter?
it does not, yeah. Yep, yeah, indentation does not matter. If it's less than 0.5, let's make it red. And then else, let's make it white. So set everybody to 1. All right, let's see if it works. Ooh, kinda. Awkward. It's an oval, right? Because what did we do? We mapped the rectangle to the square by an affine map. And affine maps take circles to ovals. And then I typed in the equation of a circle, but secretly I had already typed in an affine map before that. So the composition of those two draws an oval. So we need to fix that before we get a good picture here. But that's not too bad to fix. I started with a rectangle, and then I mapped the rectangle to a square. Now I need to just turn that back. I could just add a fudge factor, right? I could just fix that by turning it back into a rectangle. I could find the aspect ratio, the ratio of the original x to the original y, and I could just stretch out my square by that amount. So let's stretch the x-axis. Let's make the x-axis bigger. So y will stay between -1/2 and 1/2. Right now, everybody's between -1/2 and 1/2 on all sides. But let's make the x window show us more of the screen so that the aspect ratio is correct. So I want to multiply the x coordinate by some number bigger than 1 by what? By 640 over 360. By iResolution.x divided by iResolution.y.
But my screen says something different.
So yeah, so that's why I'm not going to type in the numbers. I'm going to type in iResolution.x and iResolution.y. And then all of our screens will be happy. So I want to multiply just the x coordinate by that, right? I want to change just the x. I don't want to change everybody. So uv.x is going to be its original uv.x, what it used to be. And I'm going to multiply it by iResolution.x divided by iResolution.y. So I mapped everybody to the unit square. I shifted the unit square over to be centered at 0, 0. And then I'm going to rescale so that it's not the unit square anymore. And there we go. Now we have a conformal map from our pixel space to a rectangle centered at the origin. And we got the right flag. Although I didn't actually check the size of the circle, so it might not be exactly right. But okay, so this is how we draw images.
And a very nice question.
Yeah.
Sometimes when you write 1, it works, but sometimes you need to write 1.0.
Oh, thank you. Yes. Yes, thank you. There's a lot of. Oh, yes, thank you. The question was sometimes I made the point that we need to write periods all the time, but then sometimes I'm not writing a period and it's still working. Why is that? There's a bunch of strange conventions in this language, GLSL, and I'm going to try and I'm gonna try and avoid as many of the strange conventions as I can and just teach you the simplest rules every time. And the simplest rule is always write a period. Sometimes it works without a period when it's inside of a vector constructor. So if you're making a vector, it knows that inside of that vector, all the numbers have to be floats. And so it automatically turns them into floats for you. But if you do it outside of making a new vector, it never works. But inside of making a vector, it works.
But there is no place where writing a period could...
No. Yeah, you should write a period anytime you're thinking about a floating number. Like if you have an integer when you're trying, if you want something to be an integer, then you can't write a period. But anytime you want to float, you should write a period. And then I have a bunch of lazy habits because I code in this a lot. So I'll sometimes not write a period, but I'm trying to be good for y'all. So call me out. Thank you. All right, so there we go. We can draw our circle. The other thing I wanted to go back is show you there's some inbuilt functions. So we're also not going to rely on a lot of these this week. I'm gonna aim to do everything live that we write everything from scratch that we can, so we don't have to memorize a big list of like what this programming language knows about and what it doesn't. So we just wrote out the function for distance. That's not too bad. Like we can just do that every time if we wanted to. I even wrote out squaring. Like I was being super pedantic. But the computer knows about length. GLSL, in addition to like square root, sine, cosine, exponential, log, all that, it knows the function length. And I don't know if you can see on the screen, but length turned blue when I typed it. So Shader Toy knows what functions GLSL knows about. So when I typed length there, it knows it's one of these built-in functions, turned it blue. Length takes in a vector, and it tells you the length. So if I put in a 2D vector, I could take in a 2D vector, 3D vector, 4D vector. It'll measure you the length using the Pythagorean theorem. I'm going to feed in UV, and that'll measure the length for me. Aha, the picture didn't change. That means we did it right. So it's computing the Pythagorean theorem in the background for us. One reason to use something like this or use other built-in functions is when we do computations that are difficult, the people who wrote those did a very good job of writing them to be quick. So if you're doing something and you're going to do it a million times, then maybe using a function that a smart person wrote instead of, I mean, not that we're not smart, but like a person who knows how the inside of the GPU works is better than like coding your own thing. But we're not writing anything that is going to give us that bottleneck at all. Like drawing a bunch of cool fractals, drawing a bunch of hyperbolic tilings, like none of that is going to take enough computer power that it's going to slow anything down for us. So we can write everything from scratch, no problem. It's just if you join Remy's dive into asymptotic expansions of Jacobi elliptic functions that you run into some troubles. All right, okay, so there we go. That's how we draw a circle. Let's say that I want to animate the circle. I want to make the circle do something because this is not very fun. So we learned about eye resolution. That told us how to properly scale our screen. Eye time is our computer clock. This is a floating point number. It's just a single number measuring seconds. So like how long have I been yapping up here? It's for 2013 seconds since I last hit play. So that's the number that's assigned to eye time at the moment. What if I want to make my circle do something fun? I want to make my circle wiggle. I want to make my circle like pulse. Right now its radius is, what is its radius? 0.25, right? Just hard-coded right into there. Let's make a variable under dist called radius. And I could just set that equal to 0.25 for a second, and then put radius in here. Nothing will change, right? We'll still be running good. Chill. But now let's do something fun. Let's add to that a little bit of a sinusoid. So let's add like 0.1 times a sine, because that will make it go up and down by 0.1, right? So the radius will go between 0.15 and 0.35 if I do that. So plus 0.1 times sine of I time. There we go. Now our flag's having fun. We can make it faster by speed it up, like add frequency, 2.2 period times I time. I'll go twice as quick, 20 times as quick. Give it some coffee. There you go. That's too much. I can't look at that. All right. So that's how we can make things move around. We can also move the center point of the circle if we wanted to. Like, let's actually do that. Right now I'm measuring the length of UV, right? So that's measuring the distance from the center. Let's make a variable called center. It's going to be a vector, so it's going to be vec2. I'm just going to make it 0, 0 for a second, because then I can change my formula. Distance is now the distance from the center, so the length of UV minus center. Shouldn't change anything. Doesn't change anything. Good. But now let's make center do something. Let's make our circle move around. Maybe make the x-axis like sinusoidally move back and forth. So if I make the x-coordinate of center the sine of I time, now it's sliding back and forth and scaling in size. It doesn't quite look like it's going around in a circle because I have the frequencies set wrong, but there's a fun projective geometry problem for you. Set the frequencies of those two things right so that it looks perspectively like it's going around a merry-go-round. All right, are there any questions for me on anything that's been going? I know it's a lot of like just code stuff all at once, me typing on a screen. Anything I can help with? I don't think there's much in this interface. Yeah, I should say also for those of you who are more experienced coders and prefer to work in your own IDE instead of in a web interface that doesn't have lots of options, I wrote a shader toy emulator that like has all the same variables and buffers and all the stuff we're going to use in the course, and I have it on GitHub. I can help anybody after lunch like install that and use that if you want instead. It's copy pastable, so you could use anything you can put in shader toy, you can put in this, and then type it in your own IDE. So, all right, this is moving around too much. I'm gonna stop all this. Let's go back to centered at 0, radius 0.25. Nice, okay. Oh, sorry, yes?
Is there also a legal way to normalize the time?
Oh, that's a good question. Oh, sorry. Yes, the question is there a way to normalize the I time variable the way that we normalized the frag chord? I time will always just run from the start of the clock of the computer. So the way in shader toy to like start it over at 0 is the rewind button right next to the play button. If you were coding this like not in the web interface, but you were using GLSL like internal to some other program on your computer, iTime comes from the CPU and you would just reset it before it gets passed. You can like set that variable before you pass it in. But shader toy just starts it from whenever the rewind button is hit. So if I hit here, it'll go back. There we go. Now it starts over at 0. But that's about it. And it's measured in seconds. So if you wanted to rescale it, like iTime, you wanted to measure it in minutes, you'd do iTime over 60 in your code, and then it would be in minutes. Any other questions?
How do you remember to put the semicolon?
You get yelled at for 2 years by the robot, and then you remember. At least shader toy yells at you. That's one downside of coding other places. When Henry, Sabetta, me, and Remy were working on the ray marching stuff at the beginning, like you would just get a black screen, and then it would be like shader error on line 3674, and you're like, okay, where is that? It's going to be a semicolon, isn't it? It's a semicolon. All right, so now we've drawn a filled in circle. What I want to draw next is a ring. Like, maybe I want to think about the circle as like a curve, or maybe what I actually want to draw is the curve. I want to just draw the circle, like just the line. But mathematically, a line is 0-dimensional, or 1-dimensional. Sorry, I know how to count. I don't know how to count. A line is 1-dimensional. And so if I try and measure like exactly if the distance is precisely a certain amount away, what's the chance that my pixel is going to hit exactly that amount? That's not really going to happen, right? We can try it. If distance is less than rad, I colored it red. If distance is equal to rad, notation thing here, double equal sign means that you're checking for equality. So I typed 2 equal signs in a row. I have 2 numbers and I'm trying to check if they're equal. Single equal sign is setting one thing equal to another thing. 2 equal signs is checking if something is equal to another. So okay, now I want to see if it's exactly radius 0.25. Color it red. There we go. It found every pixel whose distance to the origin is precisely 0.25. And it said, oh, none of them. Great. So if you were drawing things not in this pixel-based way, you could draw a circle by maybe plotting some points on the circle, connecting them by a bunch of little tiny straight lines, and then render that to the screen. But since we're drawing in pixels, we're running the program independently pixel by pixel, and it just checks and it goes, nope, it doesn't satisfy the condition. So I need to draw not just the circle, but I need to draw some neighborhood of the circle. If I want to make it show up on the screen, I want to give myself a little window of acceptance. Like if you are between 0.24 and 0.26, color it red, instead of if you are equal to 0.25. So let's make a new variable. Let's call it thickness or epsilon, whatever you like. I'm going to make it 0.01 for a second. And then I want to replace this with a condition that will tell me if I'm between those 2 bounds. So if I'm measuring the distance to 0.25, I could take the distance minus radius is what I had before. That was negative on the inside of the circle, positive on the outside. The absolute value of distance minus radius is positive on the outside and positive on the inside, and 0 right on the circle. So like the graph of that would look, the absolute value of distance minus radius would be a graph like this. The absolute value of distance is a cone, right? Or just distance is a cone. Distance minus radius is a cone shifted down. Absolute value flips the bottom up. And then if I subtract thickness, that would give me this region right here. So if I look at the absolute value of distance minus radius, and I want to check if that is less than thickness. That will say, am I within thickness of where I'm supposed to be? And now I got my circular ring. I have a condition that says, okay, are you within 0.01 of the 0.25 radius? If so, color the pixel red. We could have some fun here, right? We could make the thickness vary. Make it sinusoidally vary a little faster. Maybe a little more. There we go. So I just changed the thickness to vary depending on eye time, and then my circle can come in and out of existence.
Can you do logical operations and or?
Oh, yes. Can
you repeat my question?
Oh. I was given only one instruction and I've failed it 100% of the time. The question is, can you do logical operations like and or and not? And yes, you can. So exclamation point is not. I think the ampersand, which I can't draw, and the ampersand again is and then the pipes is or. So you can write logical operations in your functions too. If you want to check if you are greater than 0.25 or you satisfy some other condition, you could put that in. All right, and we end at 20, right? So in 8 minutes. Awesome. So, okay, so I want to show you one more thing here. What I want to do is remove the circle and let's draw something else. Let's draw a parabola. Let's make a like baby graphing calculator. So I just want to draw y equals x squared. So I got my screen. My screen is centered at 0, 0. Because we set all that up with, this is my UV coordinates, right? Centered at 0, 0. And I want to write down the equation y equals x squared, so I want to draw this parabola. Just like that. So I can tell if a point lives on the parabola by computing the y coordinate, like y minus x squared equals 0. That's a function that would tell me when I'm on the parabola. And so I had a function like that for the circle. I could just do a little thick tube around my parabola, right? So let's replace the circle function. My distance function for the circle is going to now be, what should we do? We have uv.y minus uv.x times uv.x. That is at least the equation of the parabola, right? Let's see what happens if I just type in the equation of a parabola. Error. What did oh, I didn't give it a name. I just got excited and typed an equation. That is supposed to be distance. Oh, I still have my radius varying. Okay, so I replaced the circle equation with the equation of a parabola. Why is it so high up? Oh, is it because I'm subtracting? Is it in infrared? Yes, there we go. There we go. Yes, parabolas don't have a radius. I was drawing drawing the points that were 0.25 away from the parabola. There we go. Thank you. Thank you. Oh yeah, and center's not a part of that anymore, right? So there we go. So we have a parabola, and it doesn't look too bad. If you look at it a little closer, you can find a lot of things to complain about. It's like, one is the edges are a little pixelated. And two, the width of the parabola, although on this parabola it might not be so easy to see. Let me make the parabola a little sharper. Let's make it like minus y is 3x squared. The parabola is thicker at the bottom than it is towards the top. My circle came out perfect, right? When I did my circle, everything was good. My circle was a nice even band. The reason is the function I wrote down to define my circle was literally the distance function to the circle. Like the length from a point is literally distance. So when I said like go 0.1 away, it was 0.1 away in distance. But here the equation y minus x squared equals 0 is not the distance to the parabola. That's just the equation of a parabola. And so now I said, okay, draw me a region around the parabola where y minus x squared is between like negative 0.01 and 0.01. But that region doesn't have to be a nice Euclidean distance neighborhood because I just used a function that happens to be 0 there. So I'm drawing like two level sets of the y, like z equals y minus x squared function. One below the parabola, one above, and they're not exactly the same width around, which makes it not look so great. But for those of you who are interested in this, there is a lot of homework and there's a lot of exercises in the course notes that I wrote for people who want to continue. So the one thing you can do from this is fix the parabola, is step one of homework for people who want to like continue and try and build something. One thing you can build is here's our current parabola. If you go to my course notes, there's all the shaders are in there. And if you click over from shader to image, it shows you the code that it's running. And you can copy that into Shader Toy. So this is the same code that we just wrote. I just organized the top a little different, the UV, to make it so it fits the parabola a little nicer. Here's our parabola, not very even. You can do other shapes, like same thing if I type in any other equation, like a level set, and I want to draw like a nice figure 8 curve, and I take a neighborhood of my level set, it looks kind of bad, just like the parabola. It's thick near spots where your function is shallow. It's skinny near spots where your function's increasing quickly. Well, what do I need to do? I need to somehow compensate for the speed my function's increasing. It's the gradient of your function. So your first step in some of the homework could be read through this and you can fix that. You can calculate the gradient of the parabola. You can divide by that and you can get a nice parabola graphing calculator. Here's it applied to the figure 8, for example. So that's one direction. There's in the notes, I have a page here with a lot of homework. So the last thing I'll explain in the last 3 minutes is what you could look at if you're interested. Let's see, will it load? There's not so much homework that it takes 30 seconds to load. I don't know what it's doing. Oh, it can't load. Strange. Let's pull it up locally. Okay, well, while we're trying to fix the computer, the homework is grouped into, I put a bunch of problems because people might be interested in all sorts of different things and different skill levels. So the homework problems are grouped into 4 categories. There's checkpoints, which are, we did some examples with circles and lines and so on in the lecture. Like go in and take those shaders and make some small modifications yourself without someone telling you exactly what to do. Like find a variable, change the radius of this circle, animate this, figure out how the mouse works from the notes. Plug in mouse instead of time somewhere to have something move with that. Then there's explorations, which take the stuff we did in lecture and just like add on to those sort of shaders. And then if you're someone who has a fair amount of experience with coding and wants to do something else, there's challenge problems, and then there's 2 projects. So projects are like longer things you could work on. So just because I don't know the level of audience in the room, I want to make sure there's like exciting things for everyone, and I'll be around all afternoon, happy to like talk with people and like work on projects. So.
Did you write the URL for the homework?
Oh yes, it is. It is the same. It's on my. It should be on. I sent it to Remy, so it's on the Discord, and it's also on the same as the course notes. So shader.stevejtrettel.site. That has everything. There's like a page for day 1, page for day 2, and so on. So the homework is just on the website there. Yeah, thanks. All right, well, thanks everyone, and looking forward to more code.